So I recently did a video on using a variable resistor sensor or any sort of variable voltage, including variable resistance or variable current, to drive an op amp as a comparator to drive something like a transistor or a microcontroller pin so that you have a threshold of that sensor to turn something on and off, such as a nightlight turning on and off when it gets a certain level of light or dark. And the concern was immediately raised that when it's near the threshold, not quite there, but near it, it may flicker as it goes above and below and above and below. And that's true. The immediate thing you think of here is a noisy switch input, which people will think, oh, Schmidt trigger, switch debouncing, yes. Or put more simply, two thresholds. So let's say you have a voltage range from your positive to your circuit ground, just like so. And you have a certain voltage that you want to trigger on. So let's say your sensor is down here somewhere, and then boop, it goes up and you trigger. And it goes up and it comes back down. You're turning on and off and on and off and on and off, and the sensor is barely moving. A human might not even be able to detect that change in light level or whatever. It might just be electrical noise changing the voltage slightly. Maybe the sensor's not actually changing. Maybe it's just power supply ripple. But it's right there on the edge and it's turning something on and off. That's no good. But what if instead of one threshold, you had two? What if you had two thresholds and a no change zone? The voltage wiggles and wiggles and wiggles until the instant it goes here, high enough. And once it gets here, it's stable, it stays on, and even if it wiggles below, even if it goes in this bad area, it does not turn off. It has to go all the way down to here to turn off. And this doesn't have to be a large range. It could just be, the sun has begun to go down, and then, it's been going down for a few minutes, and it's gotten a little darker. Just enough that it doesn't wiggle its way in or out. There's a similar thing if you're ever playing a video game, 2D side-scroller, and you have a character, and then as your character moves, the camera moves with them. But let's say you're moving left and right a little bit to, attack this guy or whatever. It can be nauseating to have the camera just absolutely locked on the character. So they have a little window of movement. If your character only moves a little bit left and right, the camera doesn't move. You have to move a certain distance one way or the other to get the camera to move. It's the same thing. So what we want is one sensor giving out one voltage, but two different thresholds, where it has to go this high to turn it on and this low to turn it off. So the wiggles should be contained like so that if it goes high, it does not go low enough to turn it off until it goes low enough to turn it off, and then it won't go high enough to turn it back on without a major change in the sensor, or what the sensor is detecting. So, of course, in electronics, there's 800,000 different ways to do something. And my original thought was going to be a couple op amps feeding into another op amp, but then I'm like, wait, there's already a device that's incredibly cheap and ubiquitous. In fact, it is the number one, according to Wikipedia, the number one most manufactured integrated circuit in all of history, the 555 timer. It has two voltage input pins, threshold and trigger. And if you drive it as a bistable multi-vibrator, also known as a latch, or flip-flop, but it's not got a clock signal, so it's really a latch, then it behaves exactly this way. And in fact, if you look, there are circuit diagrams on the internet for a 555 timer in a bistable configuration as a Schmidt trigger for switch debouncing. Well, gee, there you go. I feel good about myself that I thought of this without having to Google it, but it's not exactly a complicated thought, so I'm not going to pat my own back too much. So let's start with the timer. We have a 555 timer. I've done videos on this that give you the full wiring, so I'm not going to worry about that. I'm just going to give you the relevant pins. We have out. This out is going to be a high or a low, which you can use to drive a transistor, microcontroller pin, whatever. It's just the same as before, high or low, on or off, true or false, 1 or 0. The only other two pins that are relevant are threshold and trigger. And let me subtitle this off and on. These are two pins. And let me also say, we'll connect our circuit ground and power. I'll go ahead and do that. So this one is 2/3 VCC, and this is 1/3 VCC, if you don't use the control pin, which we don't need. Anytime the threshold pin gets a voltage higher than 2/3 of the input power, the output turns off. It goes low. Anytime the trigger pin gets a voltage below 1/3 of the input voltage, the output turns on. It goes high. Voltage goes low on trigger, turns on. Voltage goes high on threshold, turns off. Which feels kind of backwards, but who cares? You just flip wires. Electronics doesn't care about positive, negative. So how do we get two voltages? Exactly the same way. A voltage divider and no op amps. We have our supply voltage and we have our sensor, a variable resistance. Then we plug this into two potentiometers. Here's one, here's the other, and both of those go to circuit ground. They're both fed like so, and the wiper, remember the wiper, using it as a voltage divider. So we've got a voltage divider inside, we've got two voltage dividers in a voltage divider. The wiper of one goes to trigger. The wiper of the other goes to threshold. And that's the whole circuit, like magic. So what is this? What in the world did I just do? I have two parallel voltage dividers, configurable by the user. So the user in the previous design had two potentiometers. Maybe the lower one, the one for sensitivity, to get the sensor into a working range of voltage, kind of middle voltage. Maybe it's a potentiometer. Maybe you just, based on your sensor, pick a sane voltage or pick a sane value to give a sane voltage. So maybe they have a knob, maybe they don't. But the top knob, the one knob they really had, was the one to give a voltage to trigger at. So the user would say, okay, right now is the light level I want it to turn on at. So they go in there and they turn that knob just until it turns on. And then whatever voltage it ended up being, it matched. So the sensor and the voltage divider, for whatever sensor situation the user is thinking of, such as a light level, will give a certain voltage, and then they have a knob to set that voltage and it goes into the comparator. In this case, it's basically the same thing, except the user turns the knobs just a little bit until it stops flickering. If it flickers, then they can just tweak it. Basically, if it doesn't flicker, cool. If it does flicker, then they just tweak it until it stops flickering. So it's two knobs instead of one that they have to manage. So you're not going to have a night light like this. You would just put some voltage dividers in there, use a couple diodes to split it or something, I don't know. But on an actual device in the hands of an expert, somebody that knows what they're doing, they can be expected to know what they're doing. You give them these two knobs and they can just turn them until they're right. So how does it work? Let's call the sensor resistor 1. The potentiometer is, the way it's usually implemented is you've got a long resistive element of some kind and a wiper that touches it. And as you turn the knob, it changes where it's touching it, which means one half is smaller and one half is larger, which is your voltage divider because the resistive element, it's longer, more resistance. But going through the potentiometer, ignoring the wiper, through the potentiometer is always the same value. That's why you might have a 10K ohm trim pot. And in fact, if you never connected the wiper to anything, it would just be a 10K resistor. Resistor 2 and 3. And over here, resistor 4 and 5. 2 plus 3 in ohms will always be the same no matter what. No matter what 2 is and no matter what 3 is, 2 plus 3 will always be the same because it's just the wiper moving on a resistive element, but the resistive element is always the same size, and you connect power through that. And 4 plus 5 never changes even when 4 and 5 do. So what you really have is one resistor here and two resistors in parallel. As the resistance of this changes, the voltage divider changes. So, let's say you're not changing the knobs. The knobs are wherever they are. You're not sitting there fiddling with them. The knobs are just set. So these resistors are not doing anything. So you've got a single equivalent resistance. Remember your series and parallel resistor formulas. So, if you think about the wiper, you can combine these into a series, but if you ignore the wiper, because it's going through, see? It's connected to circuit ground, not through the wiper. It's one resistor. So these two resistors in parallel are equivalent in value to, you could replace them with one resistor and you'd have the same overall resistance. So this effectively, if it's not changing, is one resistor. And this resistor is changing. That's a voltage divider. Two resistors, take the voltage in the middle, it's a voltage divider. So you've got a fixed value resistor here, whatever the parallel is, and then you've got this variable resistor, and that's the voltage divider. So essentially, you've got two voltage dividers, and each of them has a changing maximum. The minimum will always be 0, and the maximum might be 5 volts, 4 volts, 3 volts, depending on what the sensor is reading. It's going to change. But everything's linear. This is all nice, gentle, ohmic devices. Everything's nice and linear. So once again, remember, there's a certain light level. So just keep it simple. The user has one light level, or one volume, or one weight, or whatever the sensor is sensing. There's one value. that they want to be a threshold. In the original design, there was 1, and this one there's 2, but they're close together. So you just do one, then do the other. So there is a certain value that they want it to turn on at or turn off at, how bright it is in the room or whatever, right? And the sensor is going to have a certain resistance based on that value. Whatever that value is, the sensor is going to have a certain value. No matter what. No matter what's going on in your circuit, the sensor is always going to be at that exact resistance for that exact condition that it's sensing. Which means, since, again, ignore the wipers, just talking about the maximums, this resistor and this equivalent resistor for that light level will always give the same maximum voltage. The voltage divider, this spot, will always be the same voltage based on the parallel equivalent of these and whatever this is at that light level. So you have a certain voltage maximum that it's always going to be at. If the sensor has a higher resistance than that value, then there's going to be more voltage drop on the sensor, and this maximum is going to go down linearly. If the sensor has a lower resistance, then it'll have less voltage drop, and the maximum will go up linearly. So it's just stretching and compressing the voltage dividers. But there's no mayhem. It's always going up and down and up and down. It'll be higher or it'll be lower if the sensor is higher or lower. And when it's at the right spot, it'll be a certain maximum. And that's, again, you size the potentiometers so that that maximum is in the right spot. So it's not, 0.001 volts and now everything's subject to noise. So then you have 2 voltage dividers that are a known maximum value. It should actually be, maybe 3/4 of supply, because we have to get one of these up to 2/3. Now you can shrink it, actually. If you use the control pin, you can actually reduce the maximum voltage that the 555 timer is looking for. Or you can just have the sensor, have these bigger so they get more voltage drop, so you're closer to the top. But anyway, the point is, at the value the user's looking for to trigger one of these knobs, there's going to be a certain voltage here, which is the maximum voltage for the potentiometer. They turn the potentiometer, and that's a voltage divider. So they're changing what the voltage is, so they can set, at the right value, they can set one of these to 1/3 and one of these to 2/3 just by turning the knob. Turning it, they don't need to see the voltages, turn it up or down until the thing turns on or off. I'm taking 18,000 years to explain one of the simplest circuits I've ever made, just to try and be clear about this. You have a voltage divider that determines the maximum for 2 other voltage dividers, and those voltage dividers put out voltages that this triggers on. When the sensor changes its resistance, the maximum voltage goes up or down, which means the outputs here go up or down. So if the voltage here goes up, the 2 wipers voltages go up, both of these go up. If this goes down, both of these go down. They go up or down together. And that's the point. We're trying to have it trigger when it's going up or down. Anyway, I'm going to say that's the explanation, because at this point, I don't know if I've missed something. If this wasn't clear, please let me know how it wasn't clear. I can do this again without missing whatever I missed. But yes, swap out your op amp for a 555 timer, which will probably run you the same price of 1 cent or less. And you just need 2 control knobs. And you basically have a user configurable Schmitt trigger. If absolutely necessary, you can have an additional set of knobs that switches between different size potentiometers for different ranges, between bright, dark, and middle. Or if you're doing weights, you could be measuring elephants and then you could be measuring mice and have a different set of potentiometers for that. Whatever you want. That's an additional engineering challenge for your particular application. So while you're trying to figure out where that elephant came from, I'll be seeing you.